Hi, this is Mr. Zachary. This is the solution guide for the first 5 problems of MILD, problems 1 through 5. And so problem 1 is if an object is not moving, does that mean there are no forces acting on it? Not necessarily. There might not be forces acting on it, but here is a situation over here where there's a cup sitting on a table. We can think about what is touching the cup. The table is touching the cup, so it's pushing up. The force of gravity is pushing down. Now the cup isn't accelerating, so we know that those two forces are equal. But remember that forces don't mean movement. Forces mean acceleration, and only if they're unbalanced forces. Remember Newton's first law, that if an object is at rest, it will stay at rest unless there are unbalanced forces on it. That doesn't mean that there aren't any forces on it. Question 2. A mountain climber is hanging from from a rope off the side of a mountain. Here she is. The woman is hanging there. It says it's at rest. It doesn't look like she's accelerating vertically up or down. And since she's not accelerating, then the sum of the forces on her must be 0. Now, how do we know? Well, if she's not accelerating, then the forces must be equal, and she must not, some of the forces must be 0. The net force. Now, what is pulling on her? Think about first what is in contact with her. The rope. The rope is pulling up on her, and gravity. Gravity is pulling down on her. Now we know that the force of the rope and the force of gravity on her must be equal, because the sum of the forces is 0, because she's not accelerating. Question 3 is you stretch a rubber band to pull a cart. Here is a force diagram for this situation. That rubber band is pulling on the cart with 2 newtons of force. We know that the mass of the cart is 1 kilogram. Now it turns out that 7 centimeters apparently equals 2 newtons of force, which logically might make you think that 4 newtons of force is, if you pulled with the rubber band to 14 centimeters, it would be 4 newtons of force. Might be something to test. But on this question, what's the acceleration on the cart? So we know we're looking for the acceleration. We know this is what we were given. We can use Newton's second law. There is only one force horizontally on it. It's the rubber band. What I should have done is drawn a force of gravity downwards and a force of the table upwards as well. I left those off, but those are important. And but we find out that the acceleration horizontally is 2 meters per second every second for this cart. Number 4, manual weighs 100 newtons and stands on the board that weighs 200 newtons. Remember, weight is just the nickname for the force of gravity on something. So we know that the force of gravity on him is 1,000 newtons. We know that the board's force of gravity on it is 200 newtons. And we know that this support is pushing up with 850 newtons. So the sum of the forces has to be 0. It doesn't look like he's accelerating up or down. So all I did was expand out and say all the downward forces are negative, all the upward forces are positive, and we know that they have to equal 0. So we know 850 is upwards. We don't know what this force is upwards. We know that 1,000 is down and 200 is down. Doing the math, you find out that that force must push with 350 newtons. Manual's weight is 1,000 newtons. Well, weight is just the nickname for the force of gravity, and we know that we can find the force of gravity by doing m times the acceleration of an object in free fall, also known as 10 meters per second every second. So we know that 1,000 equals m times 10, and so the mass must be 100 kilograms. And finally, number 5, draw force diagrams and create numerical amounts for the forces that match the situation. Here's a book being pulled to the right. I didn't create numerical amounts, but I made these markings so that you can see what I mean. Um, Here is a book. It's being pulled to the right by a string at a constant speed. Well, if we know that there's a constant speed means no acceleration. No acceleration means the sum of the forces must be zero. So we first look at what's touching the book. Well, there's a string pulling on the book. The table is pushing on the book. There's some friction because it says it's a rough table. And gravity is pulling down on the book. So we have these four forces, and because the acceleration is zero, we know that the sum of the forces must be zero. So I made these markings. One slash means these two forces, whatever their numbers are equal. These two forces, notated with the two slashes, these two must be equal. Now they may be a different number than the vertical ones, but that one and that one must be equal. For B, we know that the book is being pushed to the right by a spring and speeding up. Here's the spring. It's on a rough table. The spring is pushing this way. Table is pushing this way. The friction is pushing that way. And gravity is pulling that way. Now, if this was a smooth table, we might not have friction at all, just so you know. Because it's accelerating, we know that the forces are not balanced, but we do know they are balanced vertically. So here are the slashes saying this is equal to this. And we know that it's accelerating to the right, so the force on the right must be bigger than the force on the left. So the force of the spring on the book must be greater than the force of friction on the book. Notice it says even though it's being pushed to the right, the arrow is indistinguishable from when it was being pulled to the right, because all that matters is the direction of the force and how you draw it. And then C, a book is sliding to the right but slowing down. Well, if it's sliding to the right, that means friction would be to the left, trying to stop it. If it's sliding and not being pushed, there isn't anything over here making it move. If there was no friction, it would just keep going and going and going at a constant speed. Again, here's the table and gravity pushing up and down on the book, and those are equal. But the force of friction is the only horizontal force. That's why it slows down.